got a little bit split.
Ours
Did it really?
Yeah.
Okay, sorry. So one of the things that's kind of interesting about dealing with sample means, you might recall that last week we were talking about sample proportions, P, and today's slides we're going to be talking about sample means. And so when you're dealing with categorical data, you work with sample proportions, but when you deal with quantitative, you deal with sample means. And it works very similarly to the proportions. So you have X bar being your mean, and we use X bar because we're talking about samples. SRS meaning a sample, that's a simple random sample, size n, and we're picking it from a large population that has a mu for a mean and sigma for standard deviation. If we know that that's true, then the mean, X bar, is the same as the population mean. So that's what the stuff here down below is saying. So the good news is if your sample is drawn from a large population, then the means are the same. And the standard deviation is sigma over the square root of n. An important thing, we use this a lot. And then the rule about the 10 times size, or 1/10 size, which depending on which way you look at it, still remains the same. You might recall that when I was talking about it, I said that the population is at least 10 times the sample. So they write it in the reverse order. For the last 4 years I've taught it the other way in red, so I still talk about it that way. Your population is 10 times. You could say that your sample is less than 1/10 of the population. And our means work similarly to our proportions. It's supposedly an unbiased estimator of our mean, and we know that the larger our sample, the less our variability, and the decrease, and you'll see this in work in a little bit, I think, decreases at the rate of the square root of n. So, for example, if you want your standard deviation to be decreased in half, you want the sample to be 4 times as large, because the square root of 4 is 2. And you're dividing by the square root of n. You can see that formula down below here. That's how the standard deviation changes. So you divide by the square root of n. If the sample is 9 times as large, then your standard deviation is 1/3 as it was before. So for example, suppose that the number of movies viewed in the last year by high school students has an average of 19.3 with a standard deviation of 15.8, and we take a simple random sample of 100 high school students. We're going to calculate the mean number of movies viewed by that by the members of that sample. So we know that the mean of our sample should be the same as the mean of our population, which would be 19.3. And that's because if we look at the number of students in the high school, let's just use our high school as an example, we have roughly 2,000 students, and the population would be at least 10 times the size of our sample. And then the standard deviation, if we're looking for that, of our sample is the same thing as taking the standard deviation divided by the square root of n. So in our case here, we would take our standard deviation, which was 15.8, and we divide it by the square root of 100. And so the square root of 100 is 10. 15.8 divided by 10, 1.58. Okay. Suppose that a population is normally distributed. So one of the things that's really important in our course is that we're always looking for this normal distribution thing. Really, that's how we use statistics. Because if you don't have a normal population where we can use the normal distribution, then that causes problems for us. So one of the things that we learned today is that we're going to talk about something called the central limit theorem. And what you'll find out is later on, if your sample size is large enough, it doesn't even matter. So that's kind of the good news. So suppose our population is normally distributed with a mean of mu and a standard deviation of sigma, then the sampling distribution will also have a normal distribution. So it doesn't really matter As long as you know the population's normal, you're good to go. And we already know about the sigma divided by the square root of n and the 10% rule. If our population comes from a normal distribution, so does our sampling distribution. Good news for us. So you can say that on your test. If you're taking a sample and they tell you the population is normal, you can say your sample's normal automatically. The central limit theorem says that if you draw a simple random sample of size n from any population, and when you're, and it should be, I think. All right. So the central limit theorem says that when it's large, the sampling distribution of the sample mean is approximately normal. And it allows us to use normal probability calculations to answer questions about the sample means from any observation, even when it's not normal. And this is, should be, I believe, n right here. No, that's not what I wanted, sorry. Back up here. This should say n. So when your sample is large. So in summary, if your population is normal, so is the sample. No matter what size your sample is. If the population distribution is not normal, then you need the central limit theorem to help you out. And this is what you want to see right here. This is kind of the important deal with the central limit theorem. If your sample size is at least 30, you're good to go. That's what they consider a quote-unquote large enough sample. Okay, so that's the big idea with sample means. So let's take a look at an example here. In our example, we want to look at the length of human pregnancies from conception to birth, and it's varying according to a distribution that is approximately normal. So they tell us, approximately normal. It has a mean of 266 days and a standard deviation of 16 days. So here's my mu, and here's my sigma. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. So you're looking for the probability that your event X is more than 270. In order to do that, the first thing that we usually do is we find a z-score. So I know that my z-score will be equal to the thing I'm talking about, 270, minus my mean, which was 266, divided by my standard deviation, which was 16. And I get a z-score of, how much? 0.25. 0.25, thank you, 0.25. Which then tells me that when I'm looking on a normally distributed situation, I'm looking for the probability that my z-score is more than 0.25. So I can type that into my calculator, normal CDF. And I usually go 0.25, comma 99. .40? Wow, okay. So 0.4013, which means over a 40% chance that that's going to occur. Note, they picked a randomly chosen pregnant lady. The word A means 1. The sample was 1.